Okay, so today we're going to go over the notes that you missed in class over stoichiometry. And I know this looks like a scary long word, but we've already done most of stoichiometry. You already know how to do most of it. We did it in the SMART stoichiometry, which you got after your last test last class. And we were doing the factor label method, which is all stoichiometry is. So knowing how to build a s'more and knowing those different skills, we can apply that to chemistry, and we can use it when learning stoichiometry. Stoichiometry is pronounced stoichiometry. If we're going to be scientists, we have to make sure that we say things correctly. So this is a unit on stoichiometry, which is just a big long word for saying that it is like measuring elements. So it comes from the combination of the Greek words stoichion, meaning element, and metron, meaning to measure. So we're just measuring different elements in a balanced equation. So if you follow along in your notebooklet, our definition of stoichiometry is the study of quantitative or measurable relationships in a chemical reaction. The notes were shared for you on Classroom, the PowerPoint slide, and the notes were shared with you on Classroom. So if you want to pause the video and go over the notes, I'm going to go kind of fast just because it is a video, but we're going to keep rolling and do the examples together so you know what to do when you come to class next. Why do we want to know what stoichiometry is? Why is it important? It is important to use stoichiometry because now you can determine the quantities of reactants and products in a reaction from the balanced equation. This is extremely important that we know how to balance equations. Last unit we worked on balancing equations, canceling our charges, and working to predict the products of different chemical reactions. Now we're going to use those same skills that we had before, and we're going to use them to balance our chemical equations to then solve mathematically the quantities of reactants and products. It's just like a recipe. It's step by step. This is how many we have. This is how many we produce. This is how many I want. This is what we're doing. We're just making a recipe, a chemical recipe that you cannot and should not eat. We use coefficients in stoichiometry. Coefficients are that big number that we use in front to balance our chemical equations. Coefficients do show the number of moles of each substance involved in the chemical reaction, but they do not indicate the actual number of grams in the substance. Our subscripts help us with the grams. Our subscripts we use to solve how many grams we have with our mass on our periodic table. They show how many moles of the substance in the reactant. And we'll go more into depth in a little bit, and I'll show you exactly what we mean. But I want to give you a few examples. In this equation between nitrogen and hydrogen gas to form ammonia, we want to know how many atoms of each one we have. So when I'm looking at nitrogen, how many atoms of nitrogen do I have? How much nitrogen? I have 2 atoms of nitrogen. Now looking at this, our subscripts means how many atoms we have. How many atoms of H do we have? It won't be 2 because I have 2 H2 molecules, but I have 3 of the H2 molecules. So how many atoms of hydrogen do I have? 6. We have 6 atoms of hydrogen on both the product and the reactant side. I have 2 atoms of nitrogen here, which means I have to have 2 on our product side. I have 6 atoms of hydrogen here, which means I have to have 6 on our product side. That is balanced, and that is conserved through stoichiometry and through our chemical equations. Another example, using that same exact balanced equation, how many molecules of each of these do I have? Molecules is how many of this one molecule I have. How many of the whole compound do I have? This, to solve our molecules, we look at our coefficients. So in this one, I have 1 molecule of N2 because there's an imaginary coefficient of 1 in front of the nitrogen. I have 3 molecules of H2, so I have 6 atoms of individual hydrogens, but I have 3 of the whole entire H2 molecule. How many molecules of ammonia do I have? If I'm looking at the entire thing, I have 2 molecules of ammonia. Another example, using that same exact balanced equations, we want to know how many moles of each substance. The moles are shown in our coefficients. So our imaginary coefficient here of nitrogen, we have 1 mole in nitrogen. How many moles of hydrogen do I have? If I use the coefficient right in front, I have 3 moles of hydrogen. Now, how many moles of ammonia do I have? 2. We have 2 moles of ammonia. Moles are these coefficients that are in front of each number. Same with the molecules. One last example using the same exact balanced equation. We want to know how many grams of nitrogen we have. To solve for the number of grams of nitrogen, we have to use our periodic table. Nitrogen, if I look at my periodic table, has roughly 14 grams, 14 grams of nitrogen. Using our factor label method, we need to find how many grams of the whole entire N2 we have. So if one atom of nitrogen, or one atom of nitrogen is 14 grams, I have to multiply by 2 to get 28 grams. For hydrogen, if we look at the periodic table, hydrogen is 1 gram per mole. I have 6 hydrogens, so I need to multiply that by 6, which means I have 6 grams of hydrogen. For ammonia, nitrogen is 14. Hydrogen is plus 1. So I have 2 nitrogen, so I do 14 times 2 equals 28. Plus 2 times 3 is 6, which would give us 34 grams of ammonia. It is the same on both sides. We have 28 grams of nitrogen on here. Oh, on this side, I have 28 grams of nitrogen on the product side. I have 6 grams of hydrogen here. I have 6 grams of hydrogen on the other side, just coming together in our synthesis reaction. Synthesis, we have to remember those type of reactions from our last unit to come together to make 34 grams. All right, a quick challenge problem. If you're following along in your notes. Which one of those 4 things we just went over were conserved? Was atoms conserved, molecules, moles, or grams? In those examples that we have, atoms and mass are conserved. We have to have the same number of atoms on the reactant side as the product side, and we have to have the same amount of them. We have to have the same number of grams on the reactants and the product side. So our atoms and our mass are conserved. But if you were looking at it, the moles and the molecules, which where we find our coefficients aren't the same on both sides. So our moles and our molecules are not conserved. But our atoms and mass are conserved, which was used in the law of conservation of mass, which we keep going back to. Now I'm going to teach you how to do some math with these numbers that we have. We're going to start with mole ratios. Mole ratio is a conversion factor that relates the amount in moles of any 2 substances involved in a chemical reaction. Amount of moles in any 2 substances, this moles is the number in front, that big coefficient number, in front of the entire compound. So we can relate, in a balanced equation, we can relate using mole ratios how many moles we have on the reactant side to how many moles on the product side, and we can even do moles to moles, mole conversions on reactant to reactant or product to product, anywhere in the balanced equation that we need. Mole ratios from this last example, bringing back the nitrogen, hydrogen to equal an ammonia gas. Our mole ratios in this equation is we have 1 mole of nitrogen here to every 3 moles of hydrogen. For every 3 moles of hydrogen we have 2 moles of ammonia. For every 1 mole of nitrogen, we have 2 moles of ammonia. We are just using our ratios of how many moles we have of each one. We can use these to compare them to each part of our balanced chemical equation. I love this stoichiometry map. I gave this to you. It'll be in your worksheet packet. It is in the front page of your notebooklet. It's even in the bins that are at your table when you're in class. We can use a stoichiometry map the entire unit. I will even give one for you on the test. We use the stoichiometry map to show where we are to where we are going. And it tells you exactly what you need to do to get the number you desire, to get to the point you desire. So on the left side here, if we look at our stoichiometry map, I divide it right down the middle. This is what we are given. This is the number that we know. And this is the side that we don't know. This is what we want to know. So if I'm doing mole ratios, I'm going to start with the moles given. It tells me, using mole ratio from our equation, what we need to do to get to moles unknown. If we had molecules, we can use Avogadro's number, mass, molar mass, volume. We do a conversion factor with volume. You can follow the line to get to wherever we want. I will show you how to use this, but this is an awesome resource that is at your fingertips for you to use. So we're going to go over mole to mole conversions using that stoichiometry map. Mole to mole conversions are the conversions of moles of one type of substance to moles of another type of substance. Those are what we just did in our mole ratios. We have to know how many moles are on this side to how many moles are on the other, what we know to what we don't know. To solve mole to mole ratios, we start with our moles given. We follow our map. This is on your map, which is right in the middle. We want to get to our moles of our unknown, so we have a one-step problem. To solve for a mole to mole problem, we are using molar ratios, which is what we just went over. We're using the coefficients in front of each compound and each part of our balanced chemical equation. So I know that's a lot of talking. We're going to do some examples, so follow along in your notes. In this example, we have hydrogen and iodide to make HI. I have my stoichiometry map at the top. My question, if 4 moles of H2 react, how many moles of hydroiodic acid will form? So what we do is we start with what we know. What I want to do is underline what I know. I know I have 4 moles of H2. I'm actually going to change that color to blue so we can see it. I have 4 moles of H2. I underline what I know. Then I'm going to circle what I want to find. I want to find moles of hydroiodic acid. Then I look at my stoichiometry map. I know I'm starting with moles, so I have moles given. I draw an arrow to where I start. That was a really bad arrow. See if I can make it better. I'm going to draw an arrow to where I start. And I'm going to draw a star to where I want to go. I want to find out moles of my unknown, moles of my hydroiodic acid. Once I have my arrow and my star drawn, I connect them. I want to get from moles given to moles unknown. I have one loop, so this is a one-step problem. So then I'm ready to tackle the problem. I start with writing what I know. I have 4 moles of H2. This is a one-step problem, so just like in our factor label method, we put our X and I draw one line. It's a one-step problem, so that's all I need to do. I'm going to draw my equal sign. Now I fill in what I need. This, think of it as on top of a 1 here, so it has its own line. We need to cancel out our units on the bottom when it's on the top, so we can cancel out our units, so we're only left with what we want. So, if I have 4 moles of hydrogen on the top, Where do I put my 4 moles of hydrogen on this line? We put it on the bottom. Looking at my molar ratio, it tells us right here we need to use molar ratio from our equation, which is the coefficients in the front. I'm going to say I have 1 mole of H2 to every, now I want to find my moles of HI, to every 2 moles of hydroiodic acid. So now I write 2 mole of HI. My equal sign is next, so I'm done. All I have to do is solve the equation. I am multiplying across the top, dividing down the bottom, so I make sure my units cancel. Moles of H2, I'm left with moles of HI. Multiply across, I have 4 times 2, so I'm left with 8 moles of HI. Let's try another one. Example number 2. Using the same exact equation that we just were given, if we have 0.8 moles of hydroiodic acid, how many moles of iodine were used in the reaction? So I underline what I know. I know I have 0.8 moles of hydroiodic acid. I need to get moles of iodide, so I'm going to circle what I want to find. Then I look at my stoichiometry map. I am given moles, so I'm going to draw an arrow to what I'm starting at. And I'm going to draw a star where I need to go. I loop to what I need to do. I have 1 loop, so this is a 1-step problem. So I write down what I know. 0.8. Try again. I have 0.8 moles of hydroiodic acid. I have a 1-step problem, so I draw my multiplication sign, I draw my line, and my equal sign. Now it says on my map that I need to use molar ratio from my equation. I have moles of hydroiodic on the top, so I need to get moles of HI on the bottom. I want to find moles of iodide, so I'm going to put moles of I2 on the top. Then I fill in my numbers. How many moles of hydroiodic acid do I have in the reaction? 2. I have 2 moles given to me by my coefficient for every 1 mole of iodine. My equal sign is next, so I make sure my units cancel. Moles of HI, moles of HI. I'm left with moles of I2. Whatever's left on the top right before your equal sign has to be the same as the thing you circled. It is the same for me, so I have 0.8 divided by 2 times 1, so it would just be 0.8 divided by 2 would equal 0.4 moles of I2. Now, I'm going to give you time to try out a problem on your own. In this equation, we have hydrogen and oxygen forming water. If there are 1.3 moles of water formed, how many moles of oxygen were used in the reaction? So if you could pause the video and you can try it on your own, I'm going to keep going and solve the equation for us. If I have 1.3 moles is what I'm starting with, so that's what I know of water. I want to get moles of oxygen. So I start with my 1.3 moles of water, H2O, multiplication. It's a 1-step problem based on our stoichiometry map. I want to cancel out my moles of water, so I write that on the bottom. And I have my moles. I want to find moles of O2 on the top. Going from my balanced chemical equation, I have 2 moles of water. I have 1 mole of oxygen. I solve this, and I get 0.65 moles of O2. We make sure that we're always writing our units, or else we're going to mess up. And in my answer, I circle my answer with my appropriate units. There's another try it out problem right underneath it. Give it a shot. If 0.21 moles of H2 react, how many moles of water will form? I'm going to go ahead and solve this over here. I'm given 0.21 moles of H2 based on my stoichiometry map. I know it's a one-step problem. I want to cancel out my moles of H2 on the bottom. I want to solve. This is what I'm given. This is what I want. I want to solve for moles of water. So I'm given moles of H2O on the top. Using my molar ratio from my balanced chemical equation, I have 2 moles of hydrogen for every 2 moles of water. I solve for that. That would equal 0.21 moles of water. Circle my answer. All right, we're going to keep moving on in our notes to go over mass-to-mass conversions. Feel free to stop the video and work on worksheet number 1. You will be able to do all of worksheet number 1 with those mole-to-mole ratios. We're going to keep going in our notes, so feel free to pause the video and go over that on your own time, but we're going to keep going. Mass-to-mass conversions. Mass-to-mass conversions is when you're given the mass of one substance and you're asked to determine the mass of another. So you're going from mass to mass. Just like we went from moles to moles, we're going from mass to mass. We're changing a one-step problem into a 3-step problem. And it sounds harder, but it really isn't, as long as you follow your stoichiometry map. So to solve it, we start with our mass given. We want to go from our mass given to our moles given. And we do that by solving for the molar mass, which is on the periodic table. From our moles given, we want to get to we're going to use our molar ratio, which are coefficients, which is what we just did. We go from our moles given to our moles of our unknown. And from our moles of our unknown, we want to get the mass of our unknown using molar mass from the periodic table. If you look here, we have 1-step, 2-step, 3-step problem. So we're going to just jump right in and do some examples. So I'm given sodium plus chloride forms sodium chloride. Find the mass of table salt produced from 18.6 grams of sodium. I look at this equation, I underline what I know. I know I have 18.6 grams of sodium. I need to find the mass of our table salt, which is our NaCl. I look at my stoichiometry map. I'm starting at mass. From mass, I want to get to mass of my unknown, so I'm going to star over here. Then I'm going to figure out how I'm going to solve it. I start here. I have a 1-step. I need to get to moles again, back to mass. I have 1, 2, 3 loops, so it's going to be a 3-step problem. So now I'm going to set up my equation. I start off with what I'm given, 18.6 grams of sodium. Then I already know it's a 3-step problem, so I'm going to do 1-step, 2-step, 3-step, equal sign. So now it's all set up for me. So now I won't do less steps than I need to. I won't do more steps than I need to because I know I'm going to use 3 steps to get there. So we're going to start with what we need to do is get our molar mass from the periodic table. Molar mass is given to us grams per mole. This is a per sign, per mole. I look at my periodic table to get my grams of sodium. I have 22.99 grams of sodium. If molar mass is given to us to grams to 1 mole, I'm going to end up with a mole of sodium. And it's always in it, when we do our molar mass, it's always going to be 1 mole. Now I need to use my molar ratio, so I'm going to need to cancel out my moles of sodium. I want to get from moles of sodium to table salt, so now I need to get to my moles of table salt, so moles of NaCl. Then I'm going to have to cancel out my moles of NaCl, so I'll write it over here, of sodium chloride, to get my masses in grams of sodium chloride. So now that I know that my units are going to cancel out, I can fill in my numbers. So I already did that for sodium. I have 18.6 grams, 22.9 grams, and 1 mole of sodium. Looking at my balanced chemical equation for my molar ratio, which is what it tells us to do in this next step, I have 2 moles of sodium, so I put a 2 here, for every 2 moles of sodium chloride. And then I have to use my molar mass again to solve for mass of my unknown. So for every 1 mole, because for every 1 mole, we do 1 mole, we have grams per 1 mole. I find my molar mass of sodium chloride. Sodium has 22.99 plus chlorine, which is 35.45, which will equal 58.44 grams of sodium chloride. So then to solve it, I need to make sure that my units cancel. So I have grams of sodium, which cancels here. Moles of sodium, moles of sodium, moles of sodium chloride, moles of sodium chloride. I'm left with my grams of sodium chloride, which is what I need to find at the very end. So now I multiply across the top and divide across the bottom. So now I have 18.6 divided by 22.99 times 2 divided by 2 times 58.44, all in your calculator, which would equal 0.3. It'd be 47.28, but because of significant figures, we have in the front here, we're starting with 3 significant figures. So our answer has to have 3 significant figures. So we have 47.3 grams of NaCl. And that is our answer. Let's do another one together. And see, and if you need to work ahead, go ahead and work ahead. In my next example, I have aluminum plus iron oxide goes through a single replacement reaction to make aluminum oxide plus iron. Find the mass of aluminum oxide produced from 2.3 grams of aluminum. So, to start off, I underline what I know. I have 2.3 grams of aluminum. And I want to find the mass of aluminum oxide. So I want to find the mass of aluminum oxide. So then I see that it's a mass to mass equation. So I'm going to start with my stoichiometry map. I am given grams, so I'm given my mass of my known. And I want to get to mass of my unknown. So to get from this side to this side, I have to do 1, 2, 3-step problem. So I write down my equation. I have 2.3 grams of aluminum, of Al, is what I'm given. I have 3-step problem, so I write my factor label. 1, 2, 3, equal sign. Now I want to go through and solve my equation, but I want to cancel out my units first. So if I have grams of aluminum on the top, I need to do grams of aluminum on the bottom. Using molar mass, grams of aluminum to moles of aluminum. I need to then cancel out my moles, so I'm going to put moles of aluminum on the bottom. Using molar ratio, which is what it tells us to do right here from our equation. In this equation, it says I have 2 moles of aluminum. I want to get to aluminum oxide, so I'm going to write moles of Al2O3. It is extremely important that you keep your units so we know that they cancel out, because if you make a mistake and get the wrong answer, it's most likely because you didn't cancel out your units. So I have moles of aluminum oxide up here. I need to get moles of aluminum oxide on the bottom. And I want to end with mass of aluminum oxide using molar mass, so grams of aluminum, Al2O3. Now I'm ready to plug in my numbers. So I have grams of aluminum. I get that from the periodic table, our molar mass. So aluminum has 26.95 grams of aluminum in 1 mole of aluminum. So then I need to go to my molar ratio. My molar ratio is found from the coefficients in our balanced chemical equation. It says I have 2 moles of aluminum for every 1 mole of aluminum oxide. Then I have to use my molar mass. So I need to calculate my molar mass of aluminum, of aluminum oxide. So I have 26.95 times 2, because I have 2 aluminums, plus 16, which is the molar mass of oxygen, times 3. I'm given 101.9 grams in 1 mole of aluminum oxide. I make sure my units cancel. Grams, grams, moles, 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 moles. We're left with grams of aluminum oxide, which is what we were trying to find. I plug it into my calculator. I have 2.3 divided by 26.95 divided by 2 times 101.9. And I'm given 4.34 grams of Al2O3. If I'm looking at my significant figures, I start with 2 over here, so I would only end up with 4.3 grams of aluminum oxide. So now here are your try it out problems. We're going to try these on your own, but I will do them as an example at the bottom. Try this out on your own and try to get 1,120 grams of water, because methane burns in air in the following reaction. Methane plus oxygen equals carbon dioxide plus water. What mass of water is produced by burning 500 grams of methane? I'll get you started. We know that there's 500 grams of methane, and we want to find the mass of water. Once you do that equation, you should get 1,120 grams. That is all that I have for you today once you solve that equation. And so in class we had them work on worksheet number 1 and worksheet number 2. You should be able to do problems 1, 4, and 8 on worksheet number 2. Next class we will go over how to solve the rest of worksheet number 2, and worksheet number 1 will be due. Thank you for watching, and I'll see you in class next time.